Okay, so like I said, this next section's, it's not really new. You know, that last section with the pH calculations was definitely new, and it's the log function, which is a little bit trickier for people. This particular section should be reviewed because it's reactions with acids and bases. And we've already seen that with the double displacement. If you guys remember, there were two types of double displacements. There were the precipitation reactions and the acid-base neutralization reactions. So that's one example. So let's take a look. So acids react with metals, such as potassium, sodium, calcium, magnesium, and they produce hydrogen gas. So we've actually seen this reaction as a single displacement. You guys saw this, for example, I'll pick magnesium. If I throw magnesium into hydrochloric acid, right, how do I recognize this as a single displacement? Well, I have an element and I have a compound. And we also know that metals, when thrown in acid, give me hydrogen gas and a salt. Now, you would have to kind of know your activity, you know, look at your activity series and see if magnesium is more active than, you know, the hydrogen, which it is based on that activity series. In fact, you had several labs having you do this pretty much exact single displacement reaction. And you end up displacing a new element, which is your hydrogen gas, and then getting the salt magnesium chloride. The only thing I would need to do is balance that. So you've already seen this acid with metal reaction. It was your single displacements. We took a metal, we added to acid, and we ended up getting hydrogen gas and the salt. And you may even recall in the book, they would even, you know, there were separate sections where they would say aqueous reactions. I don't know if you guys remember that. And I was like, well, your aqueous reactions are just your double displacement and single displacement because they're in solution, aqueous. And then a lot of times they wrote out, oh, this is a gas evolution reaction. Well, some of the gas evolution reactions were single displacement and some of them were double displacement with a decomp. So I always told you, you know, remember the 5 basic types: combustion, combination, decomposition, single displacement, and double displacement, because those are a little more specific. So there's a couple examples right there, you know, and that's good too, because they're different. But in both cases, you're seeing there's a metal, you're adding it to, you know, an acid, and you're producing a salt, and specifically your hydrogen gas. So that was a very special single displacement that we talked about. And that was back, I think, in, gosh, I might have been chapter 5. So I like this one. This is the one that we saw in your gas this was recently in your lab, where you had the bicarbonate and the carbonate, and you produce CO2 gas. Is that right? You guys remember that?
Yes. Yep.
Yeah. So this one is interesting because this is essentially a double displacement coupled with the decomp. And I don't know if you guys remember me talking about this, because again, you know, those lectures, I'm not going to lie, meeting once a week on a Friday, it's tough. It was challenging, you know, it was very hard on you for 3 hours of lecture in one day. But I'll just use this one as an example, you know, where we had the HCl and let's say the calcium carbonate. And I said, oh, you could recognize that this is a double displacement. Why is it a double displacement? I have a compound and a compound, or I said it was a couple and a couple. And then you could separate it, H plus, Cl minus, Ca2 plus, because calcium is 2 plus, and the carbonate 2 minus. And remember, what do we call this? Do you guys remember what I called it?
Crisscross applesauce. Crisscross applesauce.
Yeah, well, I would call it the do-si-do, but yeah.
Oh, yeah.
The do-si-do. So there I get, you know, my calcium chloride, which you see right here. Aqueous, right? But then I had mentioned that with the double displacements, if you ever produce carbonic acid, it was an unstable intermediate that actually decomposes. And your unstable intermediates decompose to water and a gas. And that gas is whatever's left over after you subtract water from carbonic acid. So carbonic acid is H2CO3. If I take away an H2O, what's left? CO2 gas, right? Because there's one carbon and there's two more oxygens left. That's CO2. So that was one of the unstable intermediates. So this reaction we've gone over, it was called the gas evolution reaction, but I just said it was basically a double displacement, which is what this is, right? And that's how we got this. But in this particular double displacement, we have an unstable intermediate. So we have an intermediate that's unstable, and it's unstable because it's in the presence of this stronger acid, and it decomposes to water and CO2. So, yeah, someone's, I'm getting a lot of background noise. So there's a couple other unstable intermediates that break down as well. The sulfurous acid, if you ever form this in a double displacement, it decomposes into water. And what would be left over from the H2O if I subtract it from H2SO3, the sulfurous acid? SO2 gas. So that's another example of where I can produce a gas from an unstable intermediate in a double displacement. And another example would be, you guys might remember this, is the ammonium hydroxide. And if I take out water from that, which I'm going to write as HOH, it's a lot easier for me to see what's left over now, ammonia gas. So we have gone over this. It's just now we're bringing it all back. So we're going back and we're saying, oh yeah, acids react with carbonates, right? And what do they give us? Carbon dioxide, salt, and water. So here's the salt resulting from the double displacement. And then the carbon dioxide and the water are the result of the unstable intermediate, in this case, the carbonic acid breaking down to water and CO2. Now, there are other cases, but they're really emphasizing that. So we kind of have seen this before. Are there any questions with that one?
No, thank you.
And you had a lab specifically with these two. Except for, I think in your lab, it was, instead of calcium carbonate, you had sodium carbonate. And they kept the alkali metal consistent because it was in sodium bicarbonate. I think in your lab you had that. Okay. So then so we talked about going back, the single displacement reactions. Single displacements, you take a metal, you throw it in an acid, you produce hydrogen gas, right? So take a metal, throw it in acid, produce hydrogen gas and the salt. Then we just talked about, you take an acid, you throw it in with a carbonate, and a carbonate decomposes to CO2 and water. And actually, this is something I even showed, when I first showed decomposition reactions, I even showed the little triangle. If I heated up a metal carbonate, right, I get like a metal oxide and CO2 gas. Well, now, if I have it react with an acid, I'm actually getting still that CO2 gas, but I'm getting water instead of the metal carbonate. So now the other reaction that we've done is the neutralization, and these are double displacements as well. And you could have written it out as, HA plus BOH gives me HOH and BA. Why? Acid. Now, does it make sense that I write acids as HA, since we've defined them from terms of Bronsted-Lowry as what were acids, according to Bronsted-Lowry definition?
Yeah, it makes sense.
They were proton donors, right? So what do we have? we have a proton up in front. And then we have the base. Well, this is both a Braun-Sedlori base and our Arrhenius base. They release hydroxides. That's how we measure basicity in water equilibrium. And then water, and I told you to write it as HOH to help me balance it, because essentially an H plus and an OH minus come together to produce water. And then this would be your salt, which is just the conjugate base and the conjugate acid from your acid-base pairs to make the salt.